let us start this lecture with thought process. Imparting knowledge to others helps not only the initiate the lighting of others inner fire, but sustains your own fire. So, in the last lecture we basically looked at quenching diameter and quenching distance, and also derive a relationship for a quenching diameter and try to relate to the both the flame thickness and the laminar burning velocity. And today we will be looking at the flammability limits. As I had told you that there will be some limit mixtures in which beyond which the flame won't propagate. In other words, there is a limit mixture within which flame can propagate for a certain range of fuel air ratio, right. So, how to determine the flammability limit experimentally is a very important question. So, generally what happened that people use the vertical glass tube of 1.2 meter length and 50 mm of ID. Why they have gone for 50 mm? Of course, this is the American standard what people use across the globe, and because of fact that if you use a smaller diameter, what will happen? There will be some heat losses, right. If the heat losses is considerable, then you will not get the right properties related to flammability limits, right. So, that is the reason why it is being used 50 mm, where such that you do not have that problem of heat losses, right. And 1.2 meter length being so what is being done, you fill this mixed tube, which is must be transparent tube, right, or if it is not transparent, then one has to put a sensor so that you can locate the flame. It will be mixed with the certain proportion of fuel and oxidizer. So, these are being mixed first, right. Then what will happen, you ignite the flame at the bottom, then there will be kernel which will be moving, right. The flame will be moving with certain velocity of Vf, and it will be passing through, and then keep in mind that there will be because the hot gases will be on the where bottom, right, because it is coming from here. So, if it is bottom, it will be trying to expand and then moving, but if it is the top, then anyway it will be going, it will not be affecting your flame, right. So, this if it will travel at least half of the distance, right, the flame for a particular mixtures, then we call it flammable. If it will not travel much, but it will be initiated on the ignition and it will extinguish, then we call it as a basically limit mixtures. That means it has reached the limit, beyond that you cannot really make the flame to propagate. And keep in mind that the ignition source, right, or ignition energy must be good enough. Suppose you are not giving enough energy, then it is not igniting, you cannot call it as a flammability limit. Okay. The flame has to be established, and it has to it may not propagate, but it has to be established fully, right. So, that is very important. Of course, the ignition limit is also there, right. So, mixture is said to be flammable only when it travels half of the tube, 1.2 meter, that means 0.6 meter it should travel at least. But also there is some other apparatus which is being used nowadays, that is the chamber combustion pump and other things, but this is the standard one which is being used throughout the globe. And the large diameter tube is preferred as it provides consistent result, is free from the quenching, right, that I have already discussed. And direction of flame propagation affect the flammability limit because of fact that this is it is subjected to the buoyancy effect, right, because the hot gases will be trying to go up, that will be accelerating, there will be expansion. But in the case if it is, let us say there is a tube here and you are igniting the mixtures right here, this is fuel plus oxidizer, then what will happen? Flame will be traveling toward this direction. This is the downward propagation of flame, and in that case what will happen? The hot gases, these are the hot gases, right, which will be going up, it will not be affecting the flame propagation. So, therefore, that is why the limit for upward propagation are slightly wider than those of the downward direction propagation, that you will have to keep in mind. And beside this, if you look at this one, like the temperature effect, for example, T1 is here, these are the lean flammability limit, right, this lean flammability limit, and this is let us say this is your reach flammability limit, and between this lean flammability limit and the reach flammability limit, this will be flammable. That means flame can propagate and flame, you can establish flame. Beyond this thing, beyond this LFL and RFL, that is reach flammability, you cannot really establish a flame whatever the amount of initial ignition energy you give, right. And when you increase the temperature of the mixtures, right, like what will happen? There is a change in the limit, both the lean flammability limit and reach flammability. In other words, it is broadened, limits are broadened with increase in temperature, because of fact that the laminar burning velocity will be increasing, right. But if you look at the pressure effect, what will happen? If the pressure effect is to reduce the laminar burning velocity, naturally the flammability limit will be narrowed down, it will not be broadened like the temperature, that you should keep in mind. And as I told, the flammability limits varies almost linearly with the temperature. And let us look at some of the data, right, the fuel oxidizer, this is, and stoichiometric, this is the methane air, and stoichiometric 9.5%. The lean flammability limit is 5 and reach flammability is 15, that is the percentage by volume, right, and whereas the stoichiometric percent of fuel is 9.5, right. And ethane, if you look at, it is little narrowed down as compared to the methane, and if you go to the propane, it is also being narrowed down. And CO air, it is wide enough, like hydrogen air also very wider range, the flame the hydrogen air and the carbon monoxide having a wider range of flammability limit. That means it can be, flame can be established between these two range. So, therefore, one has to be very careful in handling the hydrogen and also CO, particularly hydrogen one has to, because little bit fuel being leaked out of the cylinder, it will mix with air, then it will be flammable, right. So, if you look at that way, one can give a relationship, because some people have given how to estimate this flammability limit, lean flammability limit. Lean flammability limit one can find out at as I told in the last lecture, it will be dependent on the temperature, right. So, that temperature you can look at LFLL at 25 degrees Celsius is 1 minus 0.75. This is at T, this T will be at basically 25 degrees Celsius minus 25 and divided by delta SC. Delta SC is your heat of combustion, right. And this is RFL will be similar, RFL, and these are semi empirical results, right. And RFL at 25 degrees Celsius 1 plus 0.75 T minus 25. Keep in mind that this will be delta SC right. This is being used basically within certain range of the things. And let us look at effect of pressure on the limit mixtures, right. So, if you look at the pressure is given here, pressure plotted by the different, and this is for generalized, I will be showing for the methane, and you can see that in the lean side there will be not much change, the slope is almost negligibly small here. But whereas the rich side there is a much change in the equivalence ratio, right, with the change in pressure, right. So, that means pressure has significant effect on the flammability limit, but lean side is not affected significantly by the pressure, and reach limit becomes much wider with increase in pressure. And let us look at natural gas. Yes, this is a general, it is not, data is not given, this is general trend, right, what people are saying, particularly for hydrocarbon air, right. This is hydrocarbon air mixture, hydrogen and CO, the other fuel is not, but here it is given natural. If you can look at, this is the lean side, right, it is being plotted at a different pressure, the data, right. If you look at, this is almost remaining constant, it is not constant, it is not, it is changing, but very very small change, and because of fact what people are saying, it is affected by the first order chemical kinetics, right. The order of reaction is first order reaction, whereas here this is reach limit is affected by the second order reaction, and of course, when the pressure is increasing, that become a faster, so it is remaining constant, this range, kind of thing. And keep in mind that the flammability limit is governed by the kinetics, right, unlike in stoichiometric, other like these are governed by the kinetics. And we will be looking at basically how to handle the mixture of gases. For example, you are having methane, the lean flammability limit and reach flammability limit, and let us say propane, now if there is a mixture of gases, fuel, right, and also air, and this data is experimented there, you need to find out what will be the lean flammability limit or the reach flammability limit. So, by that actually one person has given a relationship, this is known as Le Chatelier rule, right, which we will be using for that. So, this is basically Le Chatelier rule, it is known as LCR, is used to estimate limit mixtures of the multiple fuels, right. Fuel, air mixtures, if it is there, mixture. So, these will be valid particularly for the hydrocarbons, right, and this formula is like that, LFL is equal to 100 xk divided by LFL k, is a very simple formula, k is equal to 1 to n, right. X is the basically mole fractions of the constituent fuel, right. And similarly, I can have RFL is equal to 100 divided by xk into RFLK, right. This is let us say 1 and this is 2, and keep in mind that x is where x is the mole fraction of kth species. Species means basically fuel, you can say. Okay. And keep in mind that this is not valid, this relationship not valid for what? For hydrogen, CO and ethylene. Generally hydrocarbon, this Le-Chatelier rule is being valid, people have found out. So, what we will do, we will take an example just to illustrate this point. If the fuel consisting of %, by volume, of course, this is methane, and 35% of propane, ethane, C2H6, and 10, right, this would be 10% of C3H8, and of course with A, right, determined lean flammability limit or lean limit of mixture fuel and oxidizer by Le-Chatelier rule, LCR, right. So, what we will have to do, we will have to basically find out equation 2 solution. If you look at what are the things are known, XCH4 is you can say that 55 okay. So, we can find out LFL, lean flammability limit, 100 divided by XCH4 divided by LFL CH4 plus XC2S6 LFL C2S6 plus XC3H8 LFL C3H8, right. If I substitute these values, you will find out basically 55 by 5, because these are all in percentage, you will have to take care of the unit. This LFL is in percentage and these are also in percentage, right, plus 35 by 2.8 plus 10 divided by 2.1. So, you will get 3.54%, right, which is a very simple rule one can use particularly for designing purposes, and which might be having some error, but that is not much, maybe 5 to 10% error might be there, because you are just using these values and curves, right. So, having talked about this flammability limit, how to calculate for a mixture of fuel, provided you know individual lean flammability limit or the rich flammability limit data, then only you can find. So, look at this flame stabilization, because what are the conditions for the flame stabilization? We have already seen earlier that if the local velocity, right, of the fluid is equal to SL, like local laminar burning velocity, the flame will be stabilized. For example, if the flame is here which is moving with a SL and the fluid is moving with a something Vf, it is possible only when Vf is equal to SL, right. That is a very important thing. That means local gas velocity is equal to local burning velocity, right. These are all locally. If there is a gas velocity will be higher, right, if it is Vf is greater than SL, what will happen? The flame will be moving toward that, right, flame will be going away, right. And a conical flame will be established. For example, if I take, this is a basically a tube through which the fuel plus air is going, and then this is your flame surface, right. See, the flame will be moving at a velocity SL at a local surface, and it I have shown you in the earlier that the laminar burning velocity changes across this flame. Okay. In certain region it will be remaining constant here, but in this region it will be higher, and this region it will be, because this is the wall region, this is the wall stabilized, right, which will be there. So, and if it is a certain values, right, if it will exceed this velocity, if I take this some average velocity, of course there will be velocity profile, right, there will be velocity profile which will be coming over here, right, something like that. This is the parabolic profile because it is a tube and which you have given enough distance, and that will be giving, like if it is certain velocity, this velocity is increasing for the same fuel air mixture. If you are increasing the flow rate, right, if it is flow rate is increasing, what will happen? The flame will be trying to destabilize, right. Let us say this is the things, and flame may be lifted up, right, somewhere, right, there will be lift up. This is lift off height. This is known as lifted flame. If this flow rate is go on increasing further, so what will happen? Flame will go away, and then after that flame will be going away from the burn. That is known as blow off or blow out, right. But suppose you think that for the same air mixture, if the Q dot is decreasing further, so then what will happen? Flame which is established here, right, flame will come back here with the decreasing this thing, flame will be moving toward this, and when you decrease it further, right, what will happen? Flame will be coming over here, flame will be moving towards this one, this is your flame, and under this condition it is basically the flashback. When the flame is inside, this is known as flashback. As I told that earlier, the flame gets lifted up, stabilized downstream of the flame, right. This is the lifted flame, right. And with further increase in velocity, this will happen, the flame will blow out, and the flame will be blowing out, and this is known as blow off limit. And if the flame velocity is below the burning velocities of the laminar flame propagates into the burner and gets quenched, and this is known as the flashback. Right. So, this is the flame which is basically known as the flashback. Now, let us understand what is happening in the flame stabilization during the ream, because what is happening here in this case, the flame, this is the wall, right, the rim of the burners, right, this is the wall rim, right, rim of the burners, that is holding the flame, right, and it also the heat losses will take place, then flame may quench back, because once it flash back, if heat losses are more, then only it will quench, otherwise it will propagate, and that is dangerous, right. Flames should not enter into it, may devastate the things, right, because before this fuel air mixture will be there in a very big chamber, explosion may occur, right, that one has to avoid. So, now let us look at that what really, how does the flame stabilize, what is the reason. If I consider this is your burner rim, and that helps in stabilizing the flame, and this is your velocities, right, V of the fluid, right, or mixture, and this is the flame which will be moving, locally it will be moving, right, with SL, this is perpendicular that SL. If in this place it is in this region, if it is higher, then what will be happening in this case? In this region, if you look at SL, SL is high, greater than the V mixture, then what will happen? Flame will be entering into the burner, right. So, that is known as the flashback. Are you getting? But here the at this point, right, the SL is equal to V mixture. This is of course the fuel plus air, I can say, just to discuss, it can be oxidizer. So, then this is known as stable flame. Flame is stabilized at the burner rim, right, this is your rim. So, in this case what is happening? In this region the velocity is very high, which was the V mixture is greater than SL. So, therefore, the flame is going away, right, and that is known as blow out. So, I have already explained this thing, just I am repeating again. At the burner rim, flow velocity is equal to the burning velocity. Flame is likely to get stabilized here. Heat loss and radical loss to the burner rim is the cause of flame stabilization. Okay. That means what happened when the flame will be near to the wall, there will be some of the losses will be occurring, because the radical loss will be there, heat loss will be there. Laminar velocity can be obtained at the low Reynolds number, right, particularly when it is, and when the flow velocity is less than the burning velocity SL, right, flame enters into burner leading to flashback. I have already explained this thing, this is your flashback. And at critical condition, the velocity gradient, let us say at the flashback, will be when R tending towards capital R. If I consider this is the tube, if I consider, and then this will be, and is basically R at any look. So, there is a tending towards, is equal to R means it is at the wall, right, what you are considering dV by d, and this is corresponding to mixture velocity or the fluid velocity, whatever of the mixture. So, we know the because we velocity parabolic profile, so therefore, we can say V is equal to n small r square for a r is the tube radius. If you look at this, basically minus 1 by 4 mu delta L is the length of tube in which this is there, and this is you will be knowing. So, now let us look at that how we can relate this and evaluate this GF. As I told that delta P is the pressure difference across the tube length, mu is the fluid viscosity, and if you look at the flow rate, volumetric flow rate is nothing but your r 2 pi r V. I am considering V as the fluid velocity and dr, and when you put this V over here, right, you will get 0 to r 2 pi r n r square minus r square dr. When you integrate all those things, you will get basically okay, let me do that, maybe it will take little time. 2 pi n, I can take it out and integrate that thing, and then I will get r square divided by 2 minus r 4, right, by 4, and when I put this 0 to r, I will get basically pi n r 4 by 2 I will get. Okay. That means, I can write down basically n is equal to q 2 q dot divided by pi r 4. So, if I this GF, if I look at it is equal to limit r tending towards r dV by dr, I can use this again, this expression V is equal to n r square, and this thing I will get is equal to 2 r n, and if I will put this thing to sorry, this will be r tending towards 0. So, this will be 2 capital R n, and n, this is nothing but here 2 q dot by pi r square, right. That is basically I can express in terms of average velocity, right. Okay. So, if you look at q dot, basically I can say V average velocity pi by r square area, cross sectional area. If I take a tube here, right, I can take a velocity profile which is average. This is basically parabolic profile, right, but now I am considering into average because that will be a good one. This is V average, right, and this is your basically 2 r, right. The cross sectional area will be pi r square, right. And you putting that thing, you will be putting 2 4 r in q dot will be V average pi r square divided by pi r square r 4, right, pi r 4, it will be, yes, it will be 4. So, this will be cancel it out, it will be 2 pi will cancel it out, and the R also will cancel it out. I will get basically 4 V average by R is equal to 8 V average by D. That means I can get basically GF is equal to 8 V average by D. So, if you look at this gradient, I can obtain very simply conducting experiment average velocity and diameter. If I know, I can get these values. This is the diameter of tube. So, similarly you can get the gradient, velocity gradient for the blowout also, right, and which is happens to be similar in nature. I will leave that as a derivation for you to do that. Okay. Now, at the flashback, as I told, okay, this GF is equal to 8 V average, I think, all right. This is 8 V average divided by D. So, if you look at this velocity gradient, both the flashback and blowout, you can see this is for LPG air premix and it is considered for the 15 mm diameters, that is percentage of LPG is plotted here. You can see that this region, if it will go beyond, it will be flashback, and this region is a stable region, and it will go beyond, this is the blow off region kind of things, right. So, if you look at the whole regime of the Bunsen type of flame where the tube will be there, you can see that in this region you can see that is the flow velocity being plotted over the fuel oxygen ratio is the blow off which will be occurring here, right. And this is the region below which the flashback, like flashback will be occurring in this region. This will be seated flame, and this is the lifted flame what I have talked about, and this lifted flame will be oscillating. That means when you are making this flame here, let us say this is a lifted flame, when you reduce the velocity, right, this is, let us say it is having some V average here, this is having some V average, right. Then what happen, flame will be going up and coming up depending on whether it is changing V average little bit, right. So, this region, and then flame is lifted, and then it will be, of course, when you go beyond it will be blow out. And this, when you decrease these V average velocities, you can, flame can be coming back and sitting over here when the V average is reduced. This is basically drop back region. So, with this I will stop over here. In the next lecture we will be basically discussing about the ignition and ignition energy and other aspect we will be looking at it. Thank you very much.